Hey, welcome to Passages in Applied Mechanics by Dr. Lorenz Garcia. Today, statics, non-concurrent forces. A system of forces is called non-concurrent if the lines of action of the forces do not all meet a common point. See these examples. In the first one, we have a traffic light. Because the lines of action for the gravitational force and the two tension forces line up at a single point, these forces are considered concurrent. In the second one we have a table. Because the lines of action of the gravitational force and the two normal forces do not intersect at a single point, these forces are not considered concurrent. The main difference between concurrent and non-concurrent forces is that if they are exerted over free bodies, the first ones can cause translation movements, the body moves to somewhere else, whereas the second ones can do rotational movements, the body turns. For example, when driving your hands are opposite each other on the steering wheel. The forces you apply with both hands when turning either left or right cause it to turn. Both hands are involved in turning the wheel, one hand pushes while the other pulls. Similarly, when a cyclist pedals, his or her feet are parallel. One foot pushes a pedal forward while the other pushes the other pedal backward. These two forces cause the wheels on the bike to rotate. Therefore, when forces are non-concurrent, there is always a possibility that they may have a turning effect with respect to the structure or mechanical component to which they are applied. The measure of a force's turning effect about some reference point is what we call momentum of force. The moment of a force about a point is defined as the product of the force and the perpendicular distance of its line of action from the point as a product of force and distance, the moment of a force is measured in units derived from those of force and length. The international system of moment of force is the product of the Newton and the meter, called Newton meter. See, this is different from the tendency for a body to move, or translate, in the direction of the force. In order for a moment to develop, the force must act upon the body in such a manner that the body would begin to twist. Imagine two people pushing on a door at the doorknob from opposite sides. If both of them are pushing with an equal force, then there is a state of equilibrium. If one of them would suddenly jump back from the door, the push of the other person would no longer have any opposition and the door would swing away. The person who was still pushing on the door created a moment. How big is the force's turning effect? If you take your little finger and try to shut an open door with it by placing your finger near the door handle, the door would close easily. Now try to close the door with your little finger again, but this time try to push the door by placing your finger near the hinge. Does the door close as easily as when you placed your little finger near the handle? It would be much more difficult to close the door with your finger placed near the hinge. Why is that? The distance, or specifically the perpendicular distance, from the hinge to the door handle is more, which is why the force generated to produce the turning effect is more as well. We often use forces to cause an object to rotate, in other words, we need forces to create a moment. A moment can also explain why it is easier to use a longer spanner than a shorter spanner. Equilibrium of turning moments. When a structure or machine component is in equilibrium, the moments, as well as forces, must be in a state of balance, otherwise the unbalanced resultant moment would cause rotation of the body as we just seen. Thus for a body to be in rotational equilibrium, the resultant moment about any point must be equal to zero, meaning there must be no resultant turning effect. Mathematically this can be stated as a mechanical measuring scale like the one in the figure demonstrates the moment and equilibrium principle. We use scales to compare the weight of the two bodies. When the weights are imbalanced, the instrument tilts such that the scale with the heavier object will lower and the scale with the lighter object will rise. Another example is when a seesaw balances perfectly at the center. General conditions of equilibrium. It has already been established that for a system of forces to be in equilibrium, the resultant force must be equal to zero. That is, there must be no resultant push or pull. An additional condition for equilibrium of a system of non-concurrent forces must therefore ensure the absence of turning moment. Collectively, the three conditions of equilibrium are known as the three equations of statics. Let's apply these concepts to solve engineering problems. Dr. Lorenz Garcia here, thanks for watching. Ciao.